x of n is equal to a power n u of n. What is the z transform? X of z is 1 over 1 minus a z inverse, and we got the condition that mod z is greater than a. Okay. Now, let us write this in polynomial form. This will be z divided by z minus a. Do the pole 0 plot. This is the circle with radius r equal to a. There is, remember, a 0 at the origin. A 0 is marked with a circle, and there is a pole at z equal to a. Assume that z is a is real valued. Okay. So, that is the circle that passes through this. Now, this sequence is a causal sequence. Causal sequence. We will just make a note of that. It is a causal sequence. And what is its region of convergence? Its region of convergence is everywhere where mod z is greater than a. Okay, that is the region of convergence. Everywhere outside of larger than mod z greater than a. Okay. And clearly we have satisfied the condition that ROC must not include a pole, should not include a pole. Okay. Now, the key question that still remains to be answered is, why did we not take mod z less than r? That also does not include the pole, right? Why not do that? So, to answer that question, I am going to give you a second part. Okay, so this is part 2 of the same example. Okay, x of n is equal to minus a power n u of minus n minus 1. Okay, so I would like you to look at the sequence that is represented by this particular expression. Okay, so please sketch or write down the first few terms of the sequence, and then we will write down the z transform. Okay, so I hope you are comfortable writing down the first few terms. Okay, this is a non-causal sequence. N equal to 0 is 0, then the first term is minus 1 by a, minus 1 by a squared. This is corresponding to n equal to minus 1, n equal to minus 2, and minus 1 by a cubed, and so on. So, basically it is a exponential in this direction. In this case, it is on the right hand side, it is all zeros. Okay. So, I would like you to write down the z transform. X of z is equal to summation n equal to minus infinity to minus 1, because that is only region where the non-zero portions are. There is a minus sign which I can pull outside. I will get a power n z power minus n. Okay. So, I am going to write it in the following form: n equal to minus infinity to infinity a z inverse raised to the power n, and I am going to replace m with minus n. Therefore, this will become m equal to 1 through infinity, not sorry, it is not minus n, this is infinity to minus 1. Okay. So, this, when you change the variable to m is equal to minus n, it goes from 1 to infinity. A times z inverse raised to the power minus m. Okay. So, it is it's a geometric series. So, we can write it as 1 over because it starts at m equal to 1. So, you get 1 over z inverse, this is the starting term, divided by 1 minus a z inverse. Okay. Okay, you can just quickly check that this is the expression for the geometric series. Okay, simplify this. There's a minus sign, don't forget that. Then you taking the minus sign inside, you will get 1 minus a z inverse. Okay, condition for the convergence of this geometric series. Okay, anytime you want the geometric series to converge, mod a z inverse 1 over that is less than 1. Right? That's the condition that only then the powers will converge. Okay, so which you simplify, mod a z inverse is greater than 1, z mod z less than a. I hope you are able to get that, mod z less than a. So for this sequence, x of n equal to minus a power n u of minus n minus 1, which is the non-causal sequence. This has got a z transform which is given by x of z equal to 1 over 1 minus a z inverse. Compare the z transform of both those sequences. One is a causal sequence, x of z is 1 over 1 minus a z inverse. The other one is a non-causal sequence which has got the same z inverse but has got the condition that mod z less than a. Okay. So now if I choose the region of convergence as the portion that is inside the unit circle, again I cannot include the circle r equal to a, anything less than that, then what we get is the same z transform, but we will get a non-causal sequence. Okay. So here is an observation which we will come back and we will study in more detail, but I think it's a good thing for you to note down. For causal sequences, and causal sequences are a special case of right-sided sequences. For both these sequences, we will get ROC of the type, mod z greater than R1, greater than some region. In fact, maybe we can even write it as R subscript R because it's a right-sided sequence. Okay. So on the other hand, if you have left-sided sequences which includes non-causal sequences, then what you get is ROC mod z less than RL. L is basically just to denote that this is for the boundary for. So within a circle, that means it's a left-sided sequence. If the ROC is within a circle, if it is outside of a circle, it is a causal sequence, and it is something that we will study in more detail. And but this is a useful thing for you to keep in mind. Okay, so this leads us to the first important result that you must always remember with the Z transform. Okay, the Z transform of a discrete time signal is uniquely or maybe we should write it in a different way. Okay, a discrete time signal x of n is uniquely represented by the Z transform and ROC. The ROC must be specified, right? Because the Z transform is x of z and ROC must be specified, because if you saw in this previous case, the same Z transform but the one case ROC was mod z greater than A, we got as a right-sided sequence, mod z less than A, we got a left-sided sequence. So this is extremely important. You can never write a Z transform without an ROC, because if you don't write the ROC, it is not a complete answer, because you cannot then determine what the corresponding x of n is. Okay, so let's apply that and see how this is a very useful and a powerful result. So x of n is equal to 1/3 raised to the power n u of n minus 1/2 raised to the power n u of n. Okay. Two exponential sequences. We are asked to compute the Z transform. X of Z for the first term 1 over 1 minus 1/3 Z inverse, and the corresponding ROC for the blue term is mod Z greater than 1/3, mod Z greater than A. Now for the second term, it is 1 over 1 minus 1/2 Z inverse. Okay. Now, of course, you can wait a minute. I think I made a mistake here. No, minus 1. Sorry, I made a mistake here. U of minus n minus 1. Okay, so this is a left-sided sequence. So, so in this particular case, you will get the same expression, but the ROC will be mod Z less than 1/2. Okay, where are the poles of x of z? The poles are at z equal to 1/3 and z equal to 1/2. There are two poles, right? If you simplify this expression. Okay, so let's sketch it.
That should be plus, right?
I'm sorry?
That should be plus, right? X of z.
X of z, there's a minus sign here.
Because minus of a raised to n u.
Okay. Yes. Let me see. Correct. There should be a plus sign. Yeah. So this is circle with radius 1/3, circle with radius 1/2. The first term says mod z greater than 1/3. So it will be to the outside of the circle with r equal to 1/3. This is r equal to 1/3. There is a pole sitting at 1/3 and there is another pole sitting at 1/2. So what we find as the region of convergence is the one in between these two circles, but not touching either of those two circles. Okay. So for this sequence, does the discrete time Fourier transform exist? X e of j omega exists, question mark. Where is the unit circle? The unit circle is outside. This is the unit circle. This is r equal to 1. It is not part of the region of convergence, and therefore discrete time Fourier transform does not exist, meaning it does not converge uniformly. Okay, and this is also a very important example, in the sense that when you have multiple regions of convergence, what we would like to take as the ROC of x of z, ROC of x of z is the intersection of, let's call this as ROC1 and ROC2, is the intersection where both should be satisfied. Only then both will exist, and therefore x of z will also exist, is the intersection of ROC1 and ROC2. Okay. a simple extension of this particular example I would like you to consider. Okay, this is a extension of the example that we have just now looked at. Consider the sequence x of n, which has got a right-sided exponential with ratio half, 1/2 u of n, and a left-sided sequence with ratio 1/3 raised to the power n u of minus n minus 1. Okay. I would like you to find out ROC of x of z. Okay. ROC 1, what is that? It will be mod z greater than 1/2. ROC 2, mod z less than 1/3. Okay. So, the intersection of ROC 1 intersection with ROC 2 is a null set, null. So, if the ROC, there is no non-zero region of convergence, then the Z transform does not exist because there is no region of convergence. So, in this particular case, ROC does not exist. Okay. No, x of z does not exist, ROC is a null set. ROC is a null set. Okay. So, what I would like you to remember is the following. Whatever sequence is given, you can compute the Z transform from first principles. Always specify the region of convergence. If you have more than one term, there will be multiple conditions in terms of the region of convergence, and you should always look at writing down the combination or the intersection of these terms.